Looks like we are live. Hello everyone and welcome to yet another recreational programming session. How about that? Let's make a little bit of an announcement and officially start the stream as usual. What the hell has happened? Something with my keyboard. Right. So, what are we doing today? What are we doing today? Today we're doing Red Circle live on Twitch. And what are we doing on twitch.television website? Today we are doing Python string distance, right? Python string distance. I'm gonna give the link to the Twitch channel where we're doing all that. Right, twitch.tv/Toding, and I'm gonna ping everyone who's interested in being pinged. Just a second. And there we go, the stream has officially started. So the Discord is extra slow today for some reason, I don't know why. Maybe they deployed a new version, right? Some change from an intern. But yeah, hello, welcome everyone. So today we're going to be doing a little bit of a Python coding. So today I wanted to explore a little bit a very interesting algorithm that actually computes the distance between two strings. Right, so this algorithm is actually quite often used in things like Git. I think, I don't know for sure if Git actually uses that algorithm, but it has this feature where if you misspell a command, right, it actually suggests you similar commands. So how does it determine whether whatever you input is actually similar to these commands, right? So how I personally would do that, I would use something called Levenshtein Distance, right? Levenshtein Distance. I'm not sure how to spell that correctly, I'm really sorry. And this is basically the amount of actions, insertions, deletions and substitutions you have to make to the first string to get the second one, right? So, and the amount of such actions is called Levenshtein Distance, right? And the bigger, or rather, the smaller that number is, the closer the strings are to each other. Right. So, and having this sort of metric, it's super easy to come up with an algorithm that takes your input, like in the case of a Git, iterate through all of the commands and computes their Levenshtein distance and basically presents you with top 10 closest to what you try to input, and then you can pick whatever you actually want to put in there. Right. So this is a very interesting algorithm. I used it in the past for my own command line tools and stuff like that. Right, but the problem with, at least personally for me, with this algorithm is that I always treated it as a black box. I never tried to understand this algorithm. So what I usually did is essentially I would go to the Wikipedia article and I would just like copy this formula. I just put this formula into the code and simply use it as a black box without trying to understand. But the problem with that approach is that what if I have a different set of actions, right? What if I don't have substitutions? You know what I mean? Right, how do I modify this particular black box to have different sets of actions? And furthermore, the thing this algorithm gives me is the amount of actions, right? Only the amount, but it doesn't give me the specific actions. It would be kind of cool to also have an algorithm that on top of giving me the amount of, like minimal amount of actions that I have to perform, it will give me the list of those actions. That would be kind of cool, I think. And once you get the algorithm that gives you the list of actions, like where you have to insert a character or remove a character, what if you replace characters with the lines now? You would get an algorithm that computes a diff between the files. Right, I think. I'm not sure if this is the actual algorithm that is used in like diff utilities and stuff like that, but it feels like, you know, the Levenshtein distance, right? Because the patches are usually expressed in terms of like adding a line and removing a line, right? And this is basically like that, except instead of lines we use characters. But who said we have to use characters, right? So it's just like, I mean, it could be anything. It could be any sequence of objects, right? So, and that's what I want you to do today. I want you to explore this algorithm a little bit closer. Right, so we've got some subs. Thank you so much, Sina Basil, for 7 months of tier 1 subscription. Thank you with the message. I don't know why I wasn't subbed, but hi, really glad to see you. Hi. All right, so let's go and create a folder where we're going to be doing all of our shenanigans, right? So let's call it levpy, right? And let's create a file levpy. It didn't create a file for some reason. Come on, please create a file. It didn't switch to Emacs or to Python mode for some reason. I don't know why, because Emacs is broken. Just a second, I need to restart my Emacs. I need to restart my Emacs. Alrighty, so let me see. So lev.py. Finally, so what I want to do in here, I want to craft a little bit of a shebang. User bin environment Python 3, and what we're gonna do in here, we're gonna say something like hello world. Right. So we're also gonna make this thing executable, so I can now run this entire thing, and we have a little bit of a hello world. Okay, so let's try to come up with a function called lev, right, which accepts two strings, right? So s1 and s2, and should return the Levenshtein distance, right? So for now, it's not going to return anything. Right, so let's actually come up with the like strings that we want to compare. Let's try to compare things like, I don't know. So let's take something like apple, right? And for instance, to change apple to something else, we can say apple, I don't know, dapple, whatever. I don't know what that is, but it's just like the same string but with additional character, and we want this algorithm to return 1 in that specific case, right? So in the case of a sort of the same string, it should return 0, right? It should return 0. So maybe we want to actually print those things as well. Maybe we want to print those things as well. So it's quite important to remember that this is the initial string. This is like the source. And S2 is the destination. This is the string that we want to achieve by manipulating S1, right? So let's start looking at some different cases, right? So for instance, the first case that we're interested in is probably when S1 is empty, right? So we don't have anything in the initial string. So what that means? That means we have to basically add all of the characters of S2 to turn S1 to S2, right? So we initially had nothing, right? So we initially had nothing, and we have something like AAA. How to turn this string into this string? Well, we have to add A 3 times, basically the length of the second string. Makes sense? So that means the result in this particular case is going to be the length of S2. So that's the simplest case that we can have in here. That's the simplest case. So we have another sub from Великолепный Maestro. I hope I pronounced your nickname correctly. Thank you so much for tier 1 subscription with the message woo, woo, woo. All right. So, so what's the next case? So we can take a look at the case when we have something opposite, right? So when we have something opposite, for instance, when we have something in the first string, but the destination is actually empty string. So what do we do in that specific case? How can we turn this into this? Well, we can just remove all of the characters from the first string. So that means the amount of actions we have to do is the length of the first string, right? So this is basically the second query case. Right, so S2 is equal to 0, right? And then we return the length of S1, right? The length of S1. Okay, so essentially at this particular point, let me actually do something like assert false and let's say not implemented, right? Because this thing is not implemented yet. Right, so at this point, essentially, what we have is non-empty strings, right? We have non-empty strings. So the solution for the Levenshtein problem, I'm not sure if it's a correct way to say it like that. So the implementation of the Levenshtein function is usually very much recursive. So that means we can assume that we can compute the Levenshtein distance for substrings of S1 and S2, right? So essentially we have an opportunity to actually call lev on substrings of S1 and S2. For instance, we can just do that on their tail, something like that, right? And basically recursively go down and compute things on a smaller and smaller strings until one of them hits the zero. And once one of them hits the zero, we basically return the length of another one, right? So that's basically how the entire idea works. So essentially it's, I suppose it's a strategy usually called divide and conquer, right? So we have a bigger task and we split it into smaller subtasks until they become trivial, and then we return the trivial solution and then build up a more and more complex solution. Right, that's how it usually works. But I'm not sure how to take the tail of the string in Python, right? So for instance, I have something like hello, and I suppose you just put -1 at, yeah, there we go. So this is basically the tail of this entire thing, right? So I think it would be nice to actually draw a little bit, right? Draw a little bit and see what kind of stuff we can have in here. Alrighty, so essentially let's pretend that I have S1, so the initial string, and S2. So let's say this is going to be something like this. Okay. So what we want to do, we want to turn this into this, right? So somehow we want to turn this into this string. So let's try to do the following thing. What if I call lev tail of S1 and S2, right? So essentially, what if I try to compute the Levenshtein distance between the first string but with one less character to the full string? What that means? That means I'll get amount of actions. I'll get amount of actions to turn this string, so I basically removed this character from here, right? This string into this one, right? So what that means? That means it is possible to turn this string into the final one. That means this character is not really needed. So calling lev with the tail of S1 but full S2 actually indicates a removal of a character. By asking the function this sort of question, how do I turn a smallest string into the final one, you basically answer the question, how is it going to go if I remove this character? So this sort of indicates the removal. That's the removal action, right? So we can ask a different question, right? What's the S1 is full, but S2 is actually the tail, right? So how that would look like? So let's actually say that this is a removal. Remove. All right, so S1, S2. So let's put it like this. So essentially now we are taking the full S1, but we are removing one character from here. So, and we say how to turn this string into this one, right? We found the amount of actions that needs to turn this thing into this thing, but without this character. And to turn it into the full final string, we just need to add that final character. By rephrasing this question like that, we're basically defining the add action, right? So by defining the question like this, we remove a character. By defining the question like this, we add the character. You see what I mean? Right. So essentially, by just taking the substrings slightly differently, you're basically asking two different questions, like how it's going to look like when you remove a character and how it's going to look like when you add a character. Right. So does it make sense? I think it kind of makes sense. And the last thing you can do, you can actually remove the character from both of them. Right. So you can do Levenshtein S1 tail, right? S1 tail, and then S2 tail. So what does that signify? What does it even mean? What kind of question do we ask by removing both of the characters? So let's actually take a look. S1, S2. Right. So we would have something like this. And something like this. So we remove this character, and ask how do you turn this substring into this substring. So basically here we know how to turn this small string into this small string, but to get the final string we're replacing this character with this character. So this signifies a replace action. Right, so here we have a replace. And look at that, this is literally 3 different actions denoted in the original formula. These are the actions in here. We just decoded them. For instance, if you want to have different sets of actions, or for instance, if you have a problem that doesn't have a replace, you just don't have this specific case. And now you know how to sort of ask questions about different kinds of actions you can perform on the strings. Maybe you can come up with your own actions. Right, so now it is more of like a flexible system. And maybe in here you can even sort of like track the actions depending on which one you have to pick. Right, so at each point you have to actually pick a minimum between them, right, because you're optimizing, you're trying to find the minimum amount of actions. Right, so while you're trying to find a minimum, you can also keep track of which one did you pick and maybe add it to some sort of a log. And now you kind of have the list of actions that you have to perform, right? Do you know what I mean? All right. So, but there is another interesting case. When, for instance, both of the strings end with the same character. Right, so for instance, let's do it like this. So we can have a situation when both of them end with A. Right, so this is the second string. It's S1, S2. And what's interesting is that in this particular case, what we need to do, we just need to turn this substring into this substring, right? Without touching this character at all. Right, we can essentially just ignore this character. So the amount of actions that we have to perform is the amount of actions to turn this smaller substring into this smaller substring. But it only works if the two last characters are the same. Right, so this is another interesting thing. And this kind of signifies the action of ignoring the character. Right, leaving the character where it was. So you may think that you have 3 actions in here, like add, remove, and replace. In reality, you actually have 4 of them. Another one is ignore. But ignore is kind of like implied, like it's implicit, right? So, and you can encode it like this, basically. How do you take the last character of the string? I don't really remember. So probably need to do Python 3. Right, hello, and I think it's like literally -1. Yeah, it's just -1. Okay. So here we can do S1 -1 equal S2 -1. In this specific case, we can just straight up return like this thing, right? And if we got past all of these checks, we can just return the minimum of them, right? And there we go, we just implemented, we actually reinvented the whole formula that can be found in Wikipedia, but we actually went through each individual case in here and understood what each individual case does, right? So here we have 4 different actions: ignore, remove, add, and replace, right? So here they are. And now we can try to go ahead and maybe run this entire thing. So let me do, and there we go. So in the first case, we turn an apple into apple, and the amount of actions you have to do in here is actually 0. To turn apple into dapple, you actually have to do 1 action, which makes sense, right? So for instance, if you have to add additional D in here, right? which doesn't really work, right? So that's kind of interesting. So that means we made a oopsie doopsie and potentially fucky wacky. So because in all of these three actions, remove, add, and replace, we don't actually add one, right? So we take the amount of actions to turn small strings into this one, and or this down into this one, but I completely ignore that you have to like add the fact that we added or removed or replaced the character. So when we do min, we have to do +1, right? So that actually kind of makes sense. Alright, so this is 2 now, and if I remove 1d, right, so it's actually 1. I can do 1d in here, and then I can remove 1p, so which should turn this Levenshtein distance into 3, right? As you can see, it says 3, because it had to add 2 additional characters and remove 1. Right, so it had to remove 1. You can keep removing them, and it keep increasing, and so on and so forth. Okay, but it's still 4 because it basically reused that L, I suppose. Or maybe it replaced something, but yeah. So that's basically what we have in here. Does it make sense? Does it make sense, chat? I think it does make sense. I really like this algorithm. So, why +1? Because when you are taking a Levenshtein distance between a smaller substring to the bigger one, you computing the amount of actions without including the removal of that one that you just ignored. Make sense? Right, and in this case, you computing the Levenshtein distance to the smaller string without accounting that you have to add this one. And here, you also need to account the replacement. So in all of these three cases, you have to add +1. So effectively, it would be something more like +1 for each case in here, right? Because in the first case you remove a character, you need to do +1 action. In case in here you add, replace, but since you do +1 in all of the cases, it's just easier to put +1 outside of the minimum. I've never heard of this algorithm. It's very interesting. Yeah, it is also very useful, and it's used quite a lot in different applications, like you know, console applications and stuff like that, to recommend you the you know, the closest command. I already demonstrated that example, for instance, in Git. If you do something like this, right, at some point it will start recommending you, yeah, for example, I put SDF, but it thought maybe I meant ADD. So it probably computed Levenshtein distance between these two subcommands and came to the conclusion that maybe you made a typo. I don't know. If I do something like ADD D, it will still recommend D. Right, so I presume it uses Levenshtein distance, but I'm not sure, 100% sure, but it's the most logical thing to use it here. So the problem with this specific implementation of the Levenshtein distance is that it's exponential. So that means if you have strings that are like that, not that much big, right? Not that much big, it's already going to struggle to compute anything. So look how much time it takes for it to compute the distance between two strings, these two strings. So, so I'm not sure if it may be actually like taking a lot of memory, but yeah. So this is because it basically calls to the same arguments over and over again. I'm pretty sure you can actually speed it up by enabling memoization for this entire function. So as far as I know, Python has like a built-in memoization. Does anyone know? I'm pretty sure it does. Python memoization, right? So Python memoization. So what happens is that it just computes lev for the same arguments over and over again. We can actually kind of confirm that. Right, so let's actually literally just print S1 and S2 every time we're computing this thing. Right, so let's do ADD, ADDD. Right, there we go. So it actually doesn't really do that very often, like in this specific case. Right, but if we have something bigger, I think it's gonna end up with a lot of like cases that are basically the same. right? It keeps recomputing the same cases over and over again. So if I try to like copy and just search for, I probably need to do something like this. Yeah. Yeah, there we go. So these are all of the cases. So these are the arguments, and I keep scrolling through all of them. There is a lot of them, actually. Right, it keeps recomputing like the same argument over and over again. So it would be nice to basically cache some of these arguments, right, and don't recompute them over and over again, because that's basically what takes a lot of time. Right. So as far as I know, like Python has a memoization module of some sort. Right, has a memoization module. So functool cache. Okay, so let's actually try to import this into Python. So functool cache, and it works as a decorator, right? So as far as I know, it's just basically decorator. Functools cache, and let's try to run this thing now. Functools has no attribute cache, so 3.9. I don't have a 3.9, so I think the latest version of Python had 3.7. God damn it! So is there any? Okay, so there is a LRU cache. Okay, so we can use that. So LRU cache, and what do I have to do? I have to specify max size? I probably have to, but why this is not a default thing in here? I have no idea. And that was fast, relatively, I suppose. Right, so yeah, as you can see, it's super fast, and it says it's 2. Really? Well, yeah, I accidentally made it that it's actually 2. Okay, that's funny. Yeah, it has to actually remove this one and this one, right? If I take this string and I remove these things, I end up, yeah, so that's why it's 2, which makes sense, right? And you can do that on the bigger strings now, right? So, and it will work super fast, right? So we can add a little bit more in here, and yeah, now 15. But if we remove the caching in here, right? If we remove the caching, it will go forever. Right, it will go forever, well, not forever, but for a very long time, and maybe it will take up all of the memory of my like poor laptop. Probably won't. I mean, if it fits, nah, it may go too deep. But here it is super fast. Right. So you can call it a day. You can call it a day. But the most interesting thing actually arises when you try to implement this kind of cache yourself, right? This kind of cache yourself. So how can we cache that? We can just like put some sort of like a dictionary, right? Some sort of a dictionary, and where the key of the dictionary are going to be these 2 strings, and the value of the dictionary is going to be the you know, the result of this function. But we don't really have to use the strings as the key. We don't really have to use the strings as the key. So one of the way people kind of cache this sort of function is by passing the sort of like a length of the string along with the string. So yeah, as you can see in here, we take substrings all the time. Let's always put the full string as an argument here all the time, but instead of taking substrings, we're gonna pass the length of the string that we currently consider, because we always remove the character from the end, right? We always remove the character from the end. We're basically reducing the length of the string, right? So for instance, we passing a string like this, right? And then we also pass the string that points like at here. And then when we want to take a substring, we just reduce the length by 1, right? And now we are working on a smaller string, right? Now we're working on a smaller string. So maybe we want to do something like that, right? So this is how it's usually done, right? So though it's not particularly convenient now to to call this function, because on top of passing the string now, we also pass its length, right? So that means we have to copy paste it somehow. I wonder if it's possible to do some trickery in here. For instance, I know that Python supports default arguments, right? Python supports default arguments. Can I do something like this, where as a default argument I say, okay, also initialize it with the length of S1 and this one with the length of S2, you know what I mean, right? So that would be actually kind of cool. Right, so, and we don't have to pass anything in here. So let me quickly, maybe print N1 and N2, and then just return from this entire thing. Maybe return from this entire thing. So, okay, so, and S1 is not defined, so it cannot see that. Okay, so maybe we can write some sort of a wrapper, right, so that actually passes those things in there. So let's call this thing implementation. So let's replace left, maybe left like this, left impl, like so. There we go. And we're gonna have something like left S1, S2, left implementation S1, S2, length S1, length S2. Right, and that way we don't have to worry about that. So basically here, now we can assume that N1 stores the length of S1 and N2 stores the length of S2, right? So the actual length of the strings can be bigger, of course, but now we keep track of the length of the strings using a separate variable, right? So we just like separating the actual string and its length, and we keep in track of its size ourselves. So in that case, right, since now the length of S1 is N1, we can replace this thing with N1 and this one with N2, like that. Right, so now we can replace this with N2, N1. And maybe to look a little bit cool, we can put that on a single line, right? Because it's so short, it becomes so readable, so it looks cool. So here, what we're effectively doing, we're taking the last character, right? We know that N1 and N2 are not equal to 0. So to take the last character now, right, because S1 can be actually bigger than N1, but N1 is just a variable with which we're keeping track of the length now. What we have to do, we have to just do N1 minus 1 and N2 minus 2, right? So there we go. We compared the last two characters. That's what we did. So then, to take the tail of the string now, we don't really have to do this kind of stuff. What we have to do is just do N1 minus 1 and 2 minus 1, right? So does it make sense? So now, instead of taking substrings, we are reducing this the value of the variable with which we keep in track of the size of the string. So that's what we're doing now. Does it make sense? Right? Does it make sense? Hopefully that makes sense. Right, so now I need to take the substring of S1, so that means now I just have to do N1 minus 1, but keep N2 the same. Here I need to take substring of S2, I basically can keep N1 the same as it was, but N2 minus 1. And here in both of the cases, I just do N1 minus 1 and 2 minus 1. There we go. So that's basically how we refactored this entire thing, right? So we refactored this entire thing. And let's see if it actually consumes the correct thing. So I can do add daddy. So that's a good one, right? So it's a daddy now, right? So, and we don't really print anything. Okay, it's 2, right? It is 2, so it's addy should be 1 and add should be 0. But again, if these strings are too long, it's still going to be like very slow, right? It is a very slow algorithm unless you're going to try to cache it, right? So it's going to be func tools LRU cache. I'm not sure if I have to provide the max size, but it says that I have to do that, so whatever. There we go. So now it is 9, right? So but we're trying to make the cache ourselves, right? We're trying to make the cache ourselves. So now, how can we make the cache ourselves? Since now we're not keeping track of the strings, strings are always the same, we do not modify the strings, but we do modify their lengths. So what we can do now, we can use lengths as the key for the cache, as the key for the cache. How this algorithm was called to get the distance between the strings? It's called Levenshtein Distance. Right, so you can find this thing in here. Right, so I'm gonna give you the Wikipedia article, Levenshtein Distance, and also the link to the Wikipedia article is gonna be in the description for anyone who's watching on YouTube, if we're ever gonna upload that on YouTube. Right. So here's the thing. We now can use the lengths of the strings as the key for the cache, right? So, and another interesting thing is that the lengths of the strings are always going to be between like from 0 to the actual length of S1, right? Which means that we can have a two-dimensional array as the cache, where so the first row is N1 and the second and the column is N2. Right, so we can now cache all of the values of these functions within the two-dimensional array, within the two-dimensional table. Right. So, and maybe we can construct this specific table somewhere in here. Right. So let me see how you usually do that in Python. Right. So, for instance, I have the length. Or the first thing like equal 10, and the second one is going to equal to 10. So as far as I know, if you multiply by a certain value, it basically turns this into a list. So after that, I should be able to multiply that by another thing, and that turns it into another list. But as far as I know, this is actually kind of dangerous, because if you save this thing here, and then you, for instance, modify the first thing to, let's say, 69, it's gonna have 69 in each individual row, not in the first one. So because it doesn't really make copies of this thing. Right, so it's not particularly a good idea to do it like that. So as far as I know, maybe we can do something like, let's call it cache, right? So this is gonna be cache, so this is the list. And then here, I'm gonna be iterating each individual row, so that means I'm gonna be in range and 1, so this is the rows, and for each row I'm going to be just basically pushing n2 multiplied by n2. There we go. And something went wrong. I think it's more of a like append. I think it is in fact append. There we go. So this is what we have. This is the cache. And if I do 0, 0, we have a 69, and 69 is only in the first thing in here. Okay, so this is probably how we want to initialize the entire cache in here. Right. So, and what I want to do, I want to actually pass the cache as the parameter in here. Right. So we can try to pass it as a parameter. Right. So, as far as I know, when you pass it, you effectively pass it by a reference, right? So effectively pass it by a reference. So that should be fine. So here we're gonna have a cache, which is just a list. So interestingly enough, we also want to indicate that we didn't hit that cache before, right? So there's nothing in there. So maybe to emphasize that, we can probably store none there, right? None. Right, and as we hit specific caches, we're going to replace nonce with actual values, and if the function sees that actual value in there, it's just going to bring it from the cache, right? So that's going to be basically the idea. Does that make sense? That makes sense? Hopefully that makes sense. Right, well, here's an interesting thing. So when n is equal to 10, right? When n is equal to 10, it basically creates cells with the indices 0, 1, 2, 3, blah, 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 9. But what's interesting is that the argument of n1 can be equal to n1, right? So that means we need to have like an extra element in the cache to accommodate the value of n1 being equal to itself, right? So there is an extra like one element in here, right? So that's quite important, I think. So let's actually save the length in here like so. So this is going to be n2 like that. So this is going to be range. I want to add +1. And here I want to add +1 as well. So then here is going to be N1, N2, and we pass the cache in here. Quite important, we have to pass the cache everywhere in here as well. Right. We have to pass it everywhere in here as well. There we go. So let's see if it works. Right, I mean, it's super slow because we don't use the cache. We create the cache, we pass the cache, but we don't use it at all. So let's create the simple example, add and daddy, and it should be 2, right, which is correct. So everything is working and twerking correctly. Okay, so what do we want to do? What we want to do in here? We want to check if we have something in the cache, right? If cache N1 and 2 is not none, I think this is how you do that in Python. You simply return that goddamn cache, right? You simply return that. As simple as that. Okay, so if we don't have something, we want to compute that thing. So we encountered this specific corner case, right? And now we probably want to save that value to the cache and return that cache yet again, right? You see, as soon as we are returning something, we also save that to the cache. Right. The same thing goes in here as well, right? So we are saving thing in here and just returning it. For some reason, Emacs doesn't really work well with Python, so I don't know what's up with that. Okay, so this one is also interesting. So effectively, when we do a recursive call, right, we instantly save it to the cache and only then return the cache, N1 and N2. Okay, and this one is a little bit more interesting. So yeah, I think we can simply save that in the cache as well. Just return, put it like this, and then return the cache. Then return the cache. Okay, good. So that should be it. So let's see if we didn't break anything. Okay, so it's still 2, and now let's see if this monstrosity works. And it does works. I think it was 9, was it? I think it was 9. It will be kind of cool to be able to disable the cache. Can we disable the cache? I think we can effectively disable the cache by removing this thing, right? So if essentially it will always like put the stuff in the cache, right? But it's never gonna use it, right? It always saves in the cache, but it never pulls stuff out of the cache. So we can just basically enable and disable our custom cache by removing these 2 lines. I think that makes sense. Right. So let me see. So this one doesn't work. So the reason why I'm trying to do that is because I want to compare the cache of the functools LRU cache, right? So this is max size none, right? And just see if it is correct. Something unhashable. God damn it! I should have created like 2 versions. I should have created 2 versions that so we can compare them together. All right. So maybe I should really create like a second one, right? Because I want to be sure that everything's you know, works according to the standard, right? Okay. So let's call it a reference, maybe Levenshtein reference. Right, so here I'm going to be returning this entire thing, then returning N1, right, then returning this thing, then returning this thing. Okay, so yeah, this is more of a like a comparison, right? Because we want to compare these things. This thing doesn't need any cache because it has its own sort of cache, right? So right. So, and we're gonna have a reference in here and our own thing with our own cache. Does it work correctly? Missing 2 arguments. So that means I also need a bootstrap function that accepts all of that stuff in here. You know what? I think this version is going to be the one with like strings in here. I think that will make sense. Okay. So length equal to 0, so it means it's a length s2. Length s2 equal to 0. Length s1. Right. So, and this is basically the last 2 things. If they're equal, we just do -1, -1. That is not needed. -1, the same thing. -1, same thing. And this is both of them. All right. So, oh, and it also refers to these things. So it has to actually refer to reference in here. Okay. So yeah, they are the same. They are the same, as you can see. Right. So the first one is a reference, and the second one is you know, our own thing with our own cache, which is the table. So the most interesting thing would be how cache changes over time, right? So let's actually take a look. Like every time we add something to the cache, maybe we want to print that. You know what I mean? Let's actually print that. I think it's going to be really interesting. So every time we just add something in there, let's see what's inside of it, right? So we can do print cache, print cache, and then here also print cache. Let's see what's going on. But it's kind of difficult to see what the hell is going on. It would be kind of nice to pre-print that. Right, so I don't remember, like Python did have like a pre-printing stuff. Pre-print, so let's actually see. So I think it literally had import pp. No? Okay, so I mean the Google's gonna tell me. pprint. Yeah, that's right. Pprint example. All right, so this is what we have to import. So let's put it in here. And what do we have to? Why did I press Ctrl A? Indent 4. I wonder if it's gonna work with this entire thing. We'll see. We'll see. So and just pprint. Alrighty. Can I take this entire thing and simply query replace print pprint? There we go. There we go. And let's see. There we go. Okay. So this is how it goes. We started at here, right? We started at here. And we started to fill it in. So it's kind of difficult to see what's going on. I think it's going to be pretty chaotic, right? It's going to be pretty chaotic until it just like hits everything. But there's also something weird in here. There's also something weird. Bob's Ware, thank you so much for 100 bits. Thank you. Really appreciate that. So it stopped at a really weird point, I think it stopped at a very weird point. Did it even call to all of these things before? I think I want to make a small break. I think I want to make a small break and make a cup of tea. Yep. All right, let's make a small break. And all right, so let's continue. So what I want to do, so the pretty print of the cache is actually kind of dumb. All right, so I would like to have something more like, you know, aligned, so to speak, right? So maybe I'm gonna create like a custom function that does that. So let's create something like maybe a dump cache or maybe trace cache. Right, so, I'm gonna put it in here. So maybe I'm gonna also put it right here, right? So this is the cache. And how we're gonna be doing all of that? So maybe I'm gonna do row in cache, right? And in here we're gonna have a column in row, right? So, and basically what we're doing here, we just print the row, but it actually depends. Maybe this has to be the element, right? So maybe item, right? If item is none, we need to print maybe something like, I don't know, dash, right? So I want to put a dash. So, but the problem here is that print always puts a new line in here, right? And if I don't want to put a new line in here, I probably have to set end to nothing, right? So this has to be end, nothing like that. Maybe also, yeah, I can actually put something like space in here. So, and then it will make it separated by spaces. Yeah, so otherwise, if it's something else, we want to just print an item, also separated by a space. So we got this up by just a second. Yes, 0401 with a message sodding a pogging. Can't stop pogging. Thank you so much. Thank you. Alrighty. So what do we got? As far as I know, there is like an inline if in a Python, right? So we can do something like dot if item is none, else item. I think that's how we do that. I don't quite remember. Python if as expression. I remember there was something like that. A conditional expression in Python. Yesu, kawaii freaking desu. Alright, show me example. If condition else. Okay, so that's a really weird one. So it's like it's a ternary operator, but right. But Python version of that, essentially. So and that enables us to compress this entire thing into a single line. Right, and in here we probably want to have something like this. Right, so, and let's get rid of the pretty printing because it doesn't really work for me. Okay. So pp print, let me see, I'm gonna query replace super quick trace cache like so, and let's see if that changed anything. That is actually way better. What would be even cooler is probably to have an extra new line at the end of this entire stuff, right? So we can see the differences in here. So as you can see, yeah, it works kind of nice. So I suppose the problem why it looks so, you know, empty is probably because we also don't print it fully, right? So let's actually try to print it even when we try to get something from the cache. Maybe this is what we're missing. No, not really. Like half of this thing is literally not used. Half of this thing is literally not used. That is rather interesting. What if we try to maybe have something like foo and food? Right. It never actually goes, but maybe that's fine. Maybe that's fine. Okay. So what if we try to have things that are longer, right? Something like this. Alright, and it's going places. It actually prints a lot of stuff. Alright. So, yeah, and it never actually goes past that specific place, that specific like diagonal, if you know what I mean. Right, that specific diagonal, which is still kind of weird, right? But it is what it is, and it isn't what it isn't. I'm just double checking everything just in case, because I have a feeling that something is wrong in here. Even though it's probably not. Probably everything is okay in here, and that's how it's supposed to work. But for some reason I have this gut feeling that maybe something is wrong in here, I don't know. Maybe it just simply never goes past there. And the reason why it never goes past that specific diagonal is because we never have to remove anything. What if we have something bigger than this, and then basically what we have to do, we have to remove a lot of characters to actually get to the final thing. Would that be the situation. So yeah, as you can see, it effectively goes below the main diagonal in here, right? So to remove the characters, if it needs to add the characters, it goes above the main diagonal, right? And it also actually like changes it a little bit, which kind of makes sense, right? But on top of that, maybe for the situation when you have to replace literally everything, it will probably visit literally yeah, that's a good example. So that's why I had this kind of feeling, right? So because I usually test this kind of things on strings that require like a full replacement. And when you do a full replacement, it will touch each individual thing. If it needs to only add things, right? If you need to only add things, it's probably gonna stay on the above side. If it needs to remove, it's gonna stay below the main diagonal, and so on and so forth. Right. So yeah, that's probably why I was a little bit confuzzled. It's a really funny word, but anyway. But here's the interesting thing, right? So cache, in our case, is just a table. And you know what's interesting about this cache is that we always compute the current cell of this table, right? The current cell of this table always based on the left neighbor, upper neighbor, or diagonal neighbor, right? It's always these three, right? So, and while computing this entire thing recursively, it will jump around, hitting different places, hitting different cells of the cache. Since it only needs these like left, upper, and diagonal neighbors, what if we skip the entire recursive process and basically iterate the table from left to right, top to bottom, computing the required value based on these specific neighbors without any recursive bullshit, just like a two-dimensional iteration, left to right, up and down. How about that? Does it make sense? Does it make sense? So that will simplify everything. So now we don't even have to think in terms of like anything recursive, right? Because it's just a table. We're computing that based on the table. Right, so this is Levenshtein implementation. So how can we even do that? I'm gonna call it like maybe back it up. I'm gonna back it up. And how we're gonna do all of that? So in this specific case, we don't even need to accept n1 and n2 because we're gonna be doing n1 as a range of S1, length of S1 plus 1, right, because we need to hit the specific value of length, and then N2 is going to be this range. And effectively what we can have in here, we can just copy-paste this as the body of that loop, and it's going to be basically the same, right? So it's going to be basically the same. Okay, so let's actually start with these specific two cases, right? If oh my god. If n is equal to 0, we just set the cache to n2. But since we cannot return from a function, we have to do actually continue. So we basically go to the next iteration. Do we need to trace the cache? Let's not trace the caches yet. Right, here in case of n2 equal to 0, we set this thing to n1 and continue. But here's an interesting thing, right? So these values basically only trigger when n1 is always equal to 0. Which probably means that we can move out these two conditions outside of this loop. For instance, for n2 in range len s2 plus 1, right, what we can do, we can say, okay, n1 is always equal to 0, right, n1 is always equal to 0, and we just set the first thing. So effectively what we do, we just set the first row of that specific table, right, because setting the first row of the table is actually trivial. Right, it's just always n2. So, and the second loop is going to be setting the column, right, for n1 in range len s 1 plus 1, we assume that n2 is equal to 0, and in here we just set n1, right? And because of that, we don't need these two conditions in here, but we'll have to start the range from 1, right? If I remember correctly how it works in Python, right? Because I don't quite remember. So this is the range. Yeah, you specify the start and you specify the stop, which is one element above the end, right? So that's basically what we have to do. So we moved these two special cases into their separate loops in here, right? So the next thing we need to do is when the values are basically equal to each other, right? All right. So here, when we need to ignore the current character, what we have to do, we just have to, you see, perform recursive call. But we don't have to do that. We can just refer back to the cache, because n1 minus 1 and n2 minus 1 is already computed at that specific moment, right? We can always compute the current cache in terms of the previous cache because it's already computed, because they always depend on the left, upper and diagonal, and we compute from left to right, top to bottom. So we always have something available in here, something already computed in there. Does that make sense? Right. So, and it's kind of equivalent to this recursive call in here. Right, it's kind of equivalent, but it's not recursive. We just basically flattened the recursion out into this like two-dimensional iterative process. Right, and since it's not a recursive process anymore, we can just continue to the next iteration, right? To the next iteration. Cool. All right, so now we compute the minimum. Right, so let's copy paste this thing in here. And in here we just have cache. Yeah. So effectively, in this iterative version, we are replacing recursive calls to just accessing the specific caches, right? Like so. Okay, this is going to be that. And 1 and 2. All right, so we're gonna put it in here, and that is basically it. So essentially, instead of doing the recursion and just like saving everything into the cache, we just compute cache directly, and then at the end of this thing, we just pull out the answer from the cache in here. So we flattened out this recursive stuff into just like this iterative process. Does that make sense? Does that make sense? Hopefully that makes sense. Right, so let us see if it's going to work. And what's funny is that now this sort of function can be kind of self-contained, in a sense that we can create the cache inside of it. We don't need sort of like a bootstrap function. Right, so we don't need a bootstrap function in here anymore. So we can put this stuff in here somewhere. All right, so I'm gonna put it like this. All right, so we just need to do it like that. So this is gonna be the cache, and here I can probably do length s1, length s2. Right, so we initialize the cache, right? Maybe we can even do some fancy stuff, if you know what I mean. Maybe not. I don't want to do fancy stuff. So just initialize the cache. We'll just do it like that. And this is going to be Levenshtein. I want to get rid of all of the other things, right? So we don't need a recursive version anymore. All right, so we don't need that. And this is going to be the final one, the one that uses this kind of cache. Right. And it seems to be working, right? So I'm just using the new version in here. Right, so, and it says it's 3, so effectively what you need to do, you need to remove the 3 of these elements, right? So then let's see, if I replace foo with food, it has to be 1. It is in fact 1, which is nice. And maybe add and daddy should be 2. Yeah, So this entire thing works. We can try to trace the cache as well, right? So after we add something to the cache, let's do trace the cache like so. And like so. And let's see how it changes. And as you can see, now the cache is not computed all over the place. The first thing we do, we first initialize the first row, as I said, so this is the first row of the cache. Then we initialize in the first column, right? And everything was initialized, the row and column. And then we're doing left and right computing the final result in here, right? As you can see, and we basically populating the full cache in here without doing any recursive process. And then we pull out the final answer out of this thing, right? So we pull out this thing out of that. So it's not going to particularly work well if we start using like big strings in here, right? So as you can see, it's just like, well, first of all, Emacs is too slow, right? So there is that. And we probably want to actually go somewhere here. Right, so it's going to be pi, and this one's going to be a bit faster, and this is 9. And as you can see, this is like not really aligned properly. I wish there was some sort of like a left pad. Yeah, by the way, Python print pad. Is there something for padding things? How can I fill out the Python string with spaces or something like that? Alrighty. Jesus Christ. Okay. L just 10. Okay, so maybe we can. Nice language, by the way. So. Alright. So, and I can do that on the entire string, right? So I can do that on an entire string, and let's say L just 3. Will that work? It's not a thing. Is that because it's from... you can do this. I have a feeling that it's from the latest thingy. So what is that? Python 3.69 or something. So what does it say? Int. Oh, it's an int object. God damn it. So we'll probably have to do something like str then in here. Yeah, boy, there we go. Look at that. It's all aligned perfectly. Isn't that cool? All right. So it's still kind of slow, which is really weird, but it is what it is. Right. Okay. Very cool guy. Right. So let's actually maybe disable the tracing. I wonder if there is like a easy way to disable the tracing. What if we had something like trace true? If trace do that, otherwise, can I just do something like def trace cache and then this and just pass? Is that something possible? Okay, so Python periodic arguments. Jesus Christ, Google. And it's gonna be like a half of an hour article about their childhood or something before actually giving. Oh my god, this is so bad. And it's so goddamn fucking slow. Okay. Okay, so this is how we do that. Alright. Alright. Cool. I good look, hello. What's up? So what I want you to do, I want you to now check if I put false in here. Yeah, it doesn't trace anything. So now I have like a sort of like a configure thing, right, where you can enable tracing or disable tracing, which is nice. Super nice. And I also want to compare these to a reference implementation, and a reference implementation also returns 9, right? So, and this is actually a very cool idea, isn't it? Right, this is a very cool idea where we initially had like a recursive solution like very recursive solution that basically repeats the same computations over and over again. And then we started to cache, memorize the function, and then we realized that the cache is essentially just a table, and we don't even need the recursive function anymore to compute, you know, the solution. We can just directly compute the caches, right? So there is a whole class of problems that are solved like that, right? So the whole class of problems, this class of problems are called dynamic programming, the dynamic programming problems. Dynamic programming. Have you guys heard about this thing? I'm pretty sure like Aguduk definitely heard about this thing. Why did you put Python in here? Are you spying on me? I mean, of course it's spying on me. Right, dynamic programming, right. So, and essentially this is the, why do you have integrals here? This is a fucking classic Wikipedia. I swear to God, you Google up something very straightforward that has to be super simple, and this is the first thing you see. Jesus fucking Christ, the Wikipedia authors, yeah, Wikipedia authors are so fucking dense, it's insane. Why the fuck would you put integral in a... I mean, I understand that it's an example. Well, I mean, dynamic programming is probably applicable in a situation when there's also integrals, but I mean, holy fucking shit. Don't use Wikipedia. Wikipedia is awful. Right, so read something like CLRS, right? So, Introduction to Algorithm. And of course, it's on Wikipedia, but anyway. So, basically, find a copy of this book, right? And there is like a whole chapter on dynamic programming in this book, explained without integrals, I don't know how to pronounce it correctly, but without any of this gatekeeping bullshit, right? Just in simple terms. But the idea is that there is a class of problems that are solved with the recursive functions, but the recursive functions with which you solve this problem tend to recompute the same shit over and over again. But then you start to cache them, and the cache basically turns into a table that you can compute without recursion, right? So the class of these kind of problems that can be solved like that, these are dynamic programming problems, essentially. Right. So, and there's a whole class of it, like there's a lot of interesting problems that are solved like that, and they're actually quite diverse problems, right? So they're very diverse problems. As you can see, sometimes they involve even integrals, out of all things, of course, to scare away people. Dynamic programming is not in coding. What is coding, and what's the difference between coding and programming? I have no idea. All right. So there is a NIRC if more. Is it in Russian? So if more are you, right? Wait a second. Yeah, probably. Well, I mean, so it's all in Russian. It's like, I mean, come on. This is an English-speaking stream. All right. Not everyone speaks Russian here. What if the language had support for tail call optimizations? I don't think it would be possible to actually do that because of this thing. I already removed recursive version, but recursive version actually did several branching calls, right? So when you have a recursion that is also like sort of like branchy and turns like into a tree, you can't apply tail call optimizations on such recursive functions, right? You can only apply tail call optimization when the call forms into a loop, right? When it's like a, you know, just a single loop without any branching. So you just can't do that. So by dynamic, I don't know what they mean by dynamic, by the way, right? So people are curious why it is called dynamic programming. Don't ask me, I have no idea, right? So ask ChatGPT, so they probably know that. Dynamic is a terrible name. Yeah, it is. It is absolutely a terrible name, but this is what they decided to call it for gatekeeping purposes. Probably for the same purpose they put in integrals into Wikipedia article about dynamic programming. Right, so those goddamn gatekeepers. Anyway. Anyway. Alright, so what do we have? So we have something like this. It's cool and all, but as I already said, we are only getting the amount of actions that you need to perform on a string, but we don't get the specific actions, right? We can't have a list of, okay, you have initial string, at that index insert this character, remove that character from that index, and so on and so forth. How can we transform this entire thing into an algorithm that spits out a list of such things, right? What's interesting is that at any given time, as already said, we know what kind of action we perform. We know what describes a certain action. So we know what this thing basically describes ignoring the current character and leaving it as it is. We know that trying to check this thing means that we're checking whether it's possible to remove this thing. We know that this is addition and this is replacement. So we kind of know. So that means we can modify that to know these specific actions. So what I'm thinking is that I have this idea. What if we also keep track a table of actions that would perform at each an individual pair of lengths of the strings, right? On top of like storing the amount of actions, we also will store the current action that we performed in there. We'll give it a try. I think it's kind of interesting actually. So this is the cache, and let's actually do something like actions, right? And let's initialize the actions. And it's going to be something like none, right, and it's going to be length s2 plus 1. And so when we're tracing this entire stuff, I think we're going to trace them together, right? So this is going to be actions, where is another trace cache? This is actions, and this is actions as well. All right. So when we trace this thing, actions. So by the way, this is why I wanted to put variadics in here. So when I disable it, I don't have to like synchronize the signatures of these things, right? So I don't have to care about that. I'm not sure if it's even important, but yeah, whatever. Okay, so what we can do in here, we're iterating rows and columns and blah blah blah. Unfortunately, it's not particularly convenient. Because I want to be able to iterate through like actual indices in here. So maybe what I have to do a range of length of this stuff. Is that a good idea? I don't know. So then later I can do something like a length of the cache row. Right, so this is a cache row and that gives me a column. So then later I can do item cache row and column, right? But then I can have a specific action, right? Because these are two-dimensional parallel arrays, aren't they? I think they are. Right, and in here, right, if all of that stuff is none, it's going to be like that. But if it's not, what we want to do is probably have maybe f string, right? What about we do f string where we just put an item in here, and also here an action in parentheses, right? So this is going to be an action in parentheses, and let's say that the width in this specific case is going to be like 5. Right, let's go back to this example. Right, let's go back to this example, and that should be fine. Though for the action, so what's going to be the type of the action? I think I want to actually, so ignore, I want the action ignore to be maybe a single character I, right? So what other actions do we have? We have add, remove, and replace, right? So we're going to have a, right? Because I need to print this entire thing, right? I need to print this entire thing, so I need to, like a compact way to represent this kind of stuff. So the remove is going to be R, and replace is already taken, like R is already taken, so maybe, what if we call it S? Right, so for substitute, right, so maybe subst, so there we go. So ignore, add, remove, and substitute, okay. Cool. So, and when the action is not initialized, we can say that maybe it has to be something like, you know, dash, right? So it's going to be simply dash. Nice. Maybe this thing can be also like a dash as well, right? And maybe that will mean that I can get rid of this thing, because, yeah, that's actually pretty cool. Yeah, I can get rid of this shit. Aha. That is very useful, I think. I do think so. Alright. So when we're tracing, we're providing the action. Okay, so now let me try this entire thing. It doesn't do anything because we disabled the tracing. Let's enable the tracing. Int object is not iterable, right? Which is kind of understandable, but not really, because it has to be a range, of course. Okay, cool. Alright, so as you can see, the cache is populated, except we don't keep track of the actions. So the actions are supposed to be in parentheses, right? Right, so they're supposed to be in parentheses. So let's actually put something in parentheses as well in here. Okay, so effectively, when n1 is equal to 0, right? N1 is equal to 0, that means we are adding new characters to reach S2, right? So that means we have to do actions N1 and 2, and the action is add, right? So we'll just do the add. So let's see how it goes, right? So for the row is adding, right? So this is add. Interestingly, so when we are at 0, 0, we're not really adding anything, right? So if you have two strings, empty string and empty string, what's the Levenshtein distance between empty string and an empty string? Right, it's just 0, and what action do you perform to get there? You don't really do anything. So what I'm thinking is that cache 0, 0 is of course 0 by itself, and the action that we perform at 0, 0 is basically ignore, right? We don't really do anything, so it kind of makes sense to me, right? And because of that, we shouldn't probably touch, right? We shouldn't probably touch the left top corner, right? So we probably want to iterate from 1. By the way, so here, I want to move this entire stuff in here. Okay. So as you can see, this is 0, right? And we ignore here, but for this thing we are adding. So, but here, if n0 and n2 is 0 and n1 is bigger than 0, that means we need to remove the characters to get to the second string. So that means the action for the second initialization in here is remove, right? It is remove. So let's actually take a look. Yeah, as you see, we keep in track. So here's ignore, here's add, and here we're just removing things. And the specific actions in this window are going to depend on what exactly we do in here, right? For instance, here we ignore the things. That means we have to do action n1 and 2 ignore. And this one is really interesting. This one is really interesting. So what we have to do is get rid of the min function, because it kind of obscures what exactly the action we took or performed. I don't know what would be the perfect verb in this particular case. So essentially the loss of information about specific action in this algorithm happens precisely in here. Like, this is precisely the place, we pinpointed the place where we lose information about specific actions, because as you can see here, we just pick the smallest one and we ignore everything else. We should get rid of that. Right, we should get rid of that. So let's assume that at the beginning, right, we just set the current cache, the current value of the cache to basically to the left, right, or actually to the upper one, effectively removing the character, right? Yeah, effectively removing the character, which means that the action n1 and n2 is remove, right? So the next thing we want to do, we want to take the thing associated with the with add and maybe compare it with the current cache. So maybe it would be a little bit easier if we saved all of these values to separate like variables, so it's a little bit easier to see what's going on. Right, so this is going to be add, this is going to be remove, this is going to be remove, and this is going to be substitute, subst. Subst. I hope subst is a good name in here. All right. So initially we put this is supposed to be remove, right? Add. Let me double check. Do we? Yeah, if we can achieve this thing from this thing, that means we removed it. Okay, so that makes sense. Remove, add, substitute. So we set the cache to remove value and we set the action to remove. Now, if the current value is bigger than add, that means we actually want to perform the add action. So we have to do the following thing. We have to reset the cache to add and action to add. But then we found out that even smaller would be if we try to substitute, right? So we change it back to substitute and we set the action to substitute, right? And after all of that, we should not forget to increment the cache by 1, right? Because we don't account for the action that we just performed. And that's basically where we restore the lost information about specific action we performed, right? So specific action we performed. And let's see if it actually does anything. So I think it does. As you can see, these are all of the actions we have in here. Right, so this ignore. Interestingly, I think we forget one trace right after we set ignore. Right after we set ignore. Okay, so now we can see how all of the actions are populated. So within a single cell, we have the amount of actions that we need to perform to turn one string into another one. But on top of that, at this specific cell, we have the action that we performed at that specific case. So basically, the last action that we performed add, right? Which kind of makes sense, right? So because we transform a string add to daddy, right? And to transform it into daddy, we have to add 2 characters. So we probably just added two characters in here, right? So now at least we know the specific actions we performed at each individual case. But here's an interesting thing. In what order did we perform all of these actions? Right, we know the last action. The last action was add. What's the action before the last one? And here is an interesting thing. Right, so add essentially looks at the left neighbor, right? At the left column. So that means if this thing is A, the previous action was this one. If it was remove, if it was remove, we would have to go in here. If it was replace, we'd have to go by diagonal. And if it was ignore, we'll also have to go by diagonal. By knowing the current action, we can restore the previous action. And since we know this action and we know what kind of thing we did in here, we can restore the previous action, and then the previous action, and then the previous action. So we can then, from this corner, from the right bottom corner, we can backtrace all of the actions that we performed and restore the list. Isn't that cool? I think it's super cool. And as you can see, so here's the thing. So to turn add into daddy, you have to only add 2 characters, right? So when you add, effectively you go to the left, right? So because add is a column -1, right? Is a column -1. So if it's A, we go to the left. I means ignore, we don't do anything. So, and we go by diagonal. I goes here, I is diagonal again, and another add. And another add goes to the left, and I goes to by diagonal. If you trace back this entire path, you only encounter 2 A's through your entire path, and all of the rest of the things are going to be ignores, which is precisely what we need to do. So we went through the entire path, and there were only 2 adds in this entire path, which is precisely what it is. Right. And what's interesting is that you won't be able to come up with this thing if you treat Levenshtein Distance algorithm as a black box. You need to disassemble that black box and understand what each individual branch does in here, associate the actions with each individual thing in here, and only then you can see, oh, you can backtrace all of the actions back. Right. You can actually restore the list of actions. Right, and also since you know what character you currently own, you can also restore like what character you have to remove, what character you have to insert, right? And then you can build a list and just present it to the user. And again, now, what if you replace the character with the line? Well, now basically you have an algorithm that takes a diff of a file, right? And I don't know if that's the same algorithm. How does diff compute the difference between the files? Does it use something similar to Levenshtein Distance? It probably does, because it makes so much sense, but maybe it's something different. I don't really know. Right, so... Okay, so we've got some bits from Enumer8. Thank you so much for 100 bits with the message. Thanks for inspiring me to actually start a graphics programming project. You're welcome, right, you're welcome. Thank you for the bits. Thank you. Right. Oh, this logic is so strange. Would never come up with it on my own. Actually, I'll tell you a little bit of a secret. I would never come up with that myself either. The only reason I came up with this idea is because I saw a similar idea before. A similar idea actually arises. I'm still not sure if that's a good verb to use in this context, but I kind of like to use it in here. A similar situation arises with BFS. Right. It's a breadth first search. Right, it is very similar. So essentially, in BFS, there is a thing called BFS tree. Right, BFS tree. Do they? I think like CLRS actually discusses like a BFS tree. So essentially, you have a wave that traverses the graph. Right, but as you go to each individual to the next node, you actually keep track of the previous node. And as soon as you hit your target, from the target, you can backtrace the whole shortest path. And it's kind of similar in that sense. So this is what kind of helped me to understand how to come up with this entire thing. But let's actually try to implement it. It's actually very interesting. Right, so but we don't really have that much time, unfortunately. Right, so but maybe I will try to do that. Okay, go. So maybe we can have something like that. So maybe we can have something like traits, right? So this is going to be like this, and we're going to start maybe with n1 and n2 equal to something, right? So maybe we're going to say, okay, n1 is equal to length of s1. And we replace 1 with 2, there we go. And we can try to do something like this, right? While n1 is greater than 0, right? And n2 is greater than 0. Both of them are greater than 0. We basically look at the actions that we have in here, so n1 and n2. If this thing is equal to add, we do one thing, right? Assert false, not implemented. Right, so if actions n1 and 2, what we had, remove. Right, so do something like add not implemented, remove not implemented, elif action n1 and 2. So subst subst not implemented elif. So the last thing that we need to check for is ignore, right? So this is ignore. I also want to check the else branch, because if we made a oopsie doopsie and potentially fucky wucky, we want to at least say that this thing was unreachable. Right, this thing was unreachable. Okay, so in case of add, let me see. If we encountered add, what I want to do, I want to take the trace and I want to basically append the add in here, right? Though, you know what, we can append the current action, right? We can append the current action. And we repeat this like very long expression too much, so maybe I'm gonna just say it's an action, like so, and we're gonna replace all of these things with just an action, like so. We keep tracing it, and then if we encountered add, we need to subtract 1 from n2 to get to the next one, right? So this is just that. Remove is basically n1 minus 1, right? So n1 minus 1. Substitute, both actually substitute and ignore is subtracting both of them. So we can actually maybe compress these two things and put this stuff in here. So yeah, and that gives us the backtrace, right? So that gives us the backtrace, but it's in a reversed order, right? So it's in a reversed order. So what we have to do, we have to actually reverse reverse the how do we do that? Is that a thing in Python? Reverse. We can do range 10. Reversed list. So, but it doesn't modify anything, right? Reversed. Return a reversed iterator, so it doesn't modify, so it actually creates a new one. Right, so we'll have to do trace. Right, and then I'm going to do list to turn it into a list, and then I want to print this entire thing. So, what kind of actions do we need to perform? So this has to be end. Okay. Okay, this one is rather interesting. So we didn't add the last action, unfortunately, which is rather weird. Right, so this is actually like the first action. I think what we didn't add, so when a thing is 0, maybe it can be equal to 0, but then how do we handle the rest of the stuff, right? So it goes like outside, right? It goes outside, but it's not particularly great. So it could become a problem in the future. All right. Because some of them, yeah, I'm not sure if that's a good idea, but yeah. So essentially, how do we even interpret these actions? So that's kind of interesting, right? How do we interpret these actions? So we have add. So we say that we ignore anything. Okay, we've got a sub. Matesef777, thank you so much for 50 months of tier 1 subscription. Thank you. So 50 with Zozi. Yeah, thank you so much. That's a lot of months, actually. That's a lot of months. Thank you so much for such a long support. That's very cool. So how many years is that? Right, so let's take a look. 4 years. Breaking 4 years. That's a lot, actually, isn't it? Yeah. Pretty epic. Thank you so much. Almost for 20, yeah. Almost for 20. So it's kind of difficult to interpret this entire thing. I would understand if we didn't have this extra action at the end. No? I would understand this stuff if we didn't have an extra action at the end. Because if it was just add, ignore, 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 add, that actually fits perfectly into what we have in here. So let's actually grab this entire stuff, right? So if it was like that, it makes perfect sense, right? Because add, you basically add at the beginning, then you ignore, 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 add, right? You ignore, and then you add y. So you would actually be able to interpret it as iterating the initial string from left to right, you know, starting from the beginning and then to the end, and either ignoring or adding or removing something, right? But something is going wrong in here, and I'm a little bit tired already, so I'm not really sure. So maybe I should make like a small break. Okay. Let me think. Let me think. I need to grab some water, right? So just a second. I'm gonna go make a break. Maybe it's gonna be like a, let's say it's gonna be 1 minute, right? So just a small break because I need to grab some water. Grabbing some water. Okay, so let me take a look at the table one more time, right? So if it's add, So I also have a feeling that it might be wrong when we have a different shape completely, right? For instance, if I do something like full bar, maybe yeah, let's actually try to do full bar. So we ignore substitute, substitute, substitute. So does it always reach the left corner? Does it always reach the left corner? I'm not really sure if it always does that. So there's also situations when, yeah, one thing is empty and we need to add additional stuff. So for instance, like if we have something like this, I think it's gonna work incorrectly to some extent. Ignore, ignore. So here we just like adding stuff. And then ignore, ignore. Alright, but let's go back to this thing. The thing is that I don't understand is like, what exactly are we ignoring in here? What exactly are we ignoring in here? Okay, let me try to append not only the action, but also the indices in here, right? Also the indices in here. Okay, let's not reverse it, right? So I want to see all of that stuff in the original form, right? I want to see all of that stuff in the original form, how we traced all of that back. So it traces back to 0, 0 anyway, right? Both of them kind of trace back to there. Okay. So if we try to go in here, so that's totally fine. It also traces back to here. If we take a look at something bigger, it sets a lot of tracing. So maybe I want to disable the tracing, right? So let's actually disable the tracing because it's just gonna just like go forever. Yeah, it always goes back to 0, 0, right? And I'm not sure if this thing is particularly useful. I'm not sure if this thing is particularly useful. So the thing that bothers me is the case of, for instance, when you just have nothing and you turn it into something. How do you even handle that? It's still handled automatically. How does it work? Wait a second. Oh, I see. You know why I was confused? Because my brain was still thinking in terms of recursive implementation. It was still thinking in terms of recursive implementation, where we had the case of if length of S1 just instantly return, equal to 0, just instantly return the length of S2, right, which completely ignores the fact that you have to perform and keep track of lengths of S2 actions. And my brain was still thinking, we need to keep track of this specific case. We need to add these like n actions. How do we add them? But this is automatically now handled by this initialization of the cache. Right. So we keep track of these special cases when one string is completely empty and another one is not already in here. And that's why everything converges into 0, 0 always. Right. So we don't even, I think, have to even worry about that. So it's just gonna work all the time, every time. I think that's actually kind of cool. Right, and because of that, we don't really have to add the last thing. And okay, so that makes sense. So let me do daddy. That makes sense. And now probably we want to try to reverse this entire thing. Does that make sense? I want to take a look at a more complex example that also involves removing the character. So we add a character, right? So let's actually do it like this. We add, right? So this is D. Then we ignore this one. Then we ignore this one. But then we substitute D with Y. So it, okay, that's actually pretty cool. All right. That's really, really cool. So essentially, you can treat these actions as iterating from 0 to 1 and just performing this action from left to right. This is so cool. Holy shit. Right. And when we add in something, we also probably have to... It would be kind of nice to tell what character we're adding, what character we're removing, and what we're substituting. You know what I mean? Right, it would be kind of nice to actually tell that. Right, so let's actually quickly try to do that. So this is going to be the action. So we're adding, but what are we adding? Let me take a look at this thing. So we need to add the last character of the S1. So I suppose it has to be something like S1 and minus 1. Right, maybe I like minus 1. Yeah, like this. So if we are removing something, we have to take S2. Right, so let me take a look. No, if we are adding, we have to use S2, but here we have to use S1. And then when we are replacing, right, when we are replacing S1 to S2. But when we are ignoring, it's kind of a different thing, right? So we probably want to have a separate action here as well. A leaf, like so. So this one is going to be ignore. And it doesn't really matter what exactly we're ignoring, right? Because they are equal. Right, they are in fact equal, so this thing has to be copied. This thing has to be copied. Okay, so now we have the specific list of actions that we have to replace. Okay, substitute. I keep forgetting, like my brain still has the old model and I'm already tired in here, so ignore. All right, add y, ignore d, substitute d with y. Aha, I did a fucky wacky apparently. Add, so I suppose I have to remove. My brain, I'm already tired. You can already clearly see that I'm already tired, but I need to finish that. Just a second. I need to gather everything I have, and we'll get there. So, when the action is add, right? When the action that add, that means we do n2, right? So, but when we add, what do we add? We add s2, which I'm an idiot, right? So because it has to be n2 minus 1. Though we can just do n2 because we already subtracted it, right? So, and in here we can do n1, right? And in here we can do whatever, actually. Right, we can use n1 in here. And this one has to be n1 and n2. Yeah, okay, I'm an idiot, right? So I'm just tired. So forgive me for such a stupid thing. Right, add d, ignore a, ignore d, substitute d with y. Precisely, precise description of what you have to do to turn add to daddy. You have to add d, right? So you add d, then you ignore a, ignore d, and substitute d with y. Holy fucking shit. So now it's actually, you know why it's so cool? You can then take this description of actions, right? And for instance, turn it into animation, right? I think it's kind of cool, right? If you want to make an animation of how you get from one string to another one, you can make a log, right? You can make a log. And then you turn it into a sequence. All right. Okay. That's pretty cool. All right, that's so cool. I really like that. And now, right, again, so I keep repeating this thing over and over again, but you can now substitute strings, characters with strings, and you basically have a diff algorithm. Isn't it cool? It's so fucking cool. This is so fucking cool. I understand that. I understand like the algorithm really well. So to the point that I can probably modify to different situation, to different use cases, so to speak, right? To different use cases. So. Should I upload that somewhere? I'm not sure if it's worth like an actual project on GitHub, so maybe I can put it into a gist. Right, so do you guys want this gist to play yourself? I mean, you can actually like reproduce that from scratch, right? Because it's purely educational thing. So it's gonna be left by, and I'm gonna just put it in here for anyone who's interested. So it's under public domain. Yeah. Create secret gist. I'm not sure if it has to be secret, so alright, I'm gonna put that in the chat, and I'm also gonna put that in the description. Right, I'm gonna put that in the description. So this is a source code. There we go. Alright, does anyone have any questions? Before I go? I think today's stream was actually rather productive, right? I learned a lot. So does anyone have any on-topic questions? it's pretty good, but it's more of a proof of concept, right? What did you expect? I mean, did you expect me to implement like a whole freaking product of something in 2 hours, or what? I didn't understand. You have too high of expectations of me. Could this be used for bytes instead of strings? Well, I mean, probably. Well, this is a wrong question. This is a completely incorrect question. This is not the right question. The right question is, why could it not be used for bytes? That's the right question. Asking wrong questions. Why could it not be used for bytes? If you think about it, there is no reason. Alright, that's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you all next time. Love you. Mwah.